So, in the last class, we talked about line graph of bipartite graphs. So, we will also consider the complement of that now, means the alpha perfection of the line graph of bipartite graphs, or the chi perfection of the complement of the line graph of perfect graphs. Sorry, line graph of bipartite graphs. So, what would be the alpha perfection of the line graph of bipartite graphs? So, we need to show that for every induced subgraph, alpha is equal to clique cover number, alpha is equal to k. You see, this every induced subgraph is not an important issue in any of these things, because they are all this so called hereditary graph classes. That means, if you take any induced subgraph, it is again in this graph, right. For instance, if for bipartite graph, it is not just the induced subgraph, any subgraph is again a bipartite graph, right. And definitely the complements are also like that. If you take line graph of a bipartite graph, if you take the induced subgraphs, it's obviously it's also coming from some subgraph of the bipartite graph, and then it's again line graph of the bipartite graph. So, you have to be careful about that part. In fact, when you talk about the perfection, this the statement of chi equal to omega, or alpha is equal to k, should work for all induced subgraphs, not just for the graph, right. That is very important. Sometimes people make that mistake of forgetting to prove for all induced subgraph it is so. So, but in the cases we are considering, it's very like obvious that, because also these subgraphs, induced subgraphs, belong to the same class we are talking. Now, let us say what does it mean by alpha, that is the maximum independent set number, cardinality of the maximum independent set stability number of the line graph of bipartite graph. What is that? In any line graph, what is the independent set? What does the independent set correspond to in maximum matching of the original, that will become the maximum independent set in the line graph, because it is the edge set which is becoming the vertices. An independent set of vertices in the line graph correspond to an independent set of edges in the original graph, right, isn't it? So, therefore, it is the maximum matching that we are talking about, the alpha of the line graph of bipartite graph. Now, what is k? What is actually the clique cover number of the line graph of bipartite graph? So, first remember what was clique. What was a clique in the line graph of the bipartite graph? It corresponds to edges. It corresponds to, because now the vertices are the edges, but the original graph, what does that? Because you have to connect the notion of the clique in the line graph with some notion in the original graph. What is that? I have already discussed this yesterday. The maximum clique correspond to maximum of what? Or essentially any clique correspond to what in that sense? Yeah, so it's essentially a clique somehow comes from the edges which are incident on the same vertex, something like this, right. In the graph, we have some situation like this, then this becomes a clique in the line graph, right, because these are all connected, all these things are adjacent to each other, right. And we have seen that except in the case of triangle, all cliques have to come from some situation like this, right. So, in bipartite graph, we do not have triangle. So, therefore, because triangle translate to triangle, I know. Otherwise, any other clique, bigger cliques are coming from this only. So, in the bipartite graph, anyway, we do not have to worry about it. So, we know that all these cliques are essentially correspond to some vertices, the collection of edges incident on some vertex in the original graph. Now, tell me what will clique cover correspond to? This is something, a question which is You have to think and tell me. What will a minimum clique cover of the line graph of bipartite graph correspond to? Because our intention is to prove that alpha is equal to k. Alpha is a maximum matching. So, what is a clique cover, the clique cover number, that means the minimum clique cover correspond to? You know what clique correspond to and what is the minimum clique cover correspond to? Think a little bit and just try to guess what it is. It is it's a vertex cover. Why it is a vertex cover? Because you are collecting vertices in the original graph, because a vertex along with its edges become the clique, right? Somehow that vertex represents the clique, though the vertex itself is not part of the clique in the line graph. It's only the collection of edges. That means this is like holding, this is the basket, right, which provides the vertices of the clique. But then you are selecting such things, vertices you are selecting in some sense, right? And what is the intention when you say clique cover? Means you should cover all the vertices of the line graph. That means you should cover all the edges of the original graph. So, we are looking for some collection of vertices which can cover all the edges. So, which is essentially the vertex cover. And when you minimize it, it will become minimum vertex cover. And this is quite interesting. That means the statement of alpha perfection for the line graph of bipartite graph turns out to be what? Maximum matching is equal to minimum vertex cover. This is our Koenig's theorem, right? So, and these kind of things of course create some interest in people, right? Because I see. So, when I study the alpha perfection of this special thing, line graph of bipartite graph, I am getting some theorem which I was studying like as a very important theorem in the beginning, right? So, it's quite much more powerful statement, this chi perfection and alpha perfection. It is capturing well-known theorems even for special classes of graphs, right? So, when I apply it to the chi perfection or alpha perfection of some specialized perfect graphs itself, I am getting some well-known theorems. So, that kind of interests people in the concept, right? So, therefore, people say, okay, let's see. So, if I can prove it completely, then I may get some bigger statement. That feeling will come, right? These kind of things definitely are motivation for studying more, right? And I hope it is fine, the line graphs. So, now what all things we have covered? We have first covered bipartite graphs and co-bipartite graphs, complement of both are perfect. Now, we have completed line graph of bipartite graphs and complements of line graphs of bipartite graphs. That means both of them are chi perfect or both of them are alpha perfect. Everything we have done. Now, I will yesterday in the tutorial session we introduced this concept of interval graphs, right? Interval graphs. Now, let us see whether they are perfect or not. Are they perfect? What were interval graphs? It is each vertex can be associated to a interval on the real line, such that whenever two vertices have an edge between them, whenever they are adjacent, what should happen for the intervals corresponding to those vertices? They should intersect. Otherwise, they should not intersect. So, that intersection of two intervals should correspond to whether there is an edge between two vertices or not. So, we saw that this kind of captures many of these scheduling problems, like yesterday we did this classroom scheduling, the lecture scheduling in classrooms, and then the coloring problems translate to be the resource, namely minimizing the resource, namely the classroom in that problem, right. So, there can be other questions, right. So, yeah, this can come in more interesting situations, like let us not get too much into that, like applications. So, if you search for applications, you will get lots and lots of them, because essentially time intervals, right, intervals can correspond to time intervals or a sequence of things. For instance, if you are generating intermediate codes in a compiler or something, you may create a sequence of statements, right, and so you may see for a particular variable. So when is it alive in that the lifespan, right? The span of that variable. So maybe you may say that from 100th line to 250th line it is used. After that, the variable may be still there. Then you need a register allocated to the variable beyond that. So you may want to say that from what duration I need that variable to get a register, right? So in such question, you can try to create a conflict graph like you did in the yesterday and ask for. So usually you need to decide how many processors I need, right? So minimum number of registers, right? So that again becomes the coloring problem, right? So this kind of lot of applications you may have to look for things and then you see many applications, because a very natural model which captures the way it happens in the real life. Okay. Now these intervals, yesterday we had seen couple of interesting properties for the intervals. What was that? It was, you proved that interval graphs do not have C4s and onwards. Chordless 4 cycles are not there, 5 cycles are not there, 6 cycles. So they are, therefore we say that they are chordal graphs, right? Chordal graph means those graphs which do not have this kind of C4, C5, C6, etc. Right? So they do not have this thing that you proved yesterday. And did you prove the coloring algorithm? Or did you check it? For instance, yesterday. So for how do you prove the chi-perfection of interval graphs? So you have to show that its chromatic number is equal to clique number. But it's important to show that for every induced subgraph also it is so. But then induced subgraph is not a big issue, because if you take an induced subgraph of an interval graph, again it's an interval graph, because the same the sub collection of intervals will work, right? Now, but did you do it yesterday? The chromatic number is equal to clique number question. Yeah, maybe you can just repeat it. So some of you might have done it. It was an algorithm, right? So you see, if the chromatic number can never go below the clique number. But if you show a coloring which uses exactly the clique number, that omega number of colors, then what does it mean? You have done the best, right? So if you get a graph and you demonstrate a coloring using exactly the clique number of colors, omega number of colors, then it should be the optimum, right? Because you cannot do better, right? Because omega itself is a lower bound for that. You cannot do better than that. So that's what we are going to do, right? So suppose you have an interval graph here. Let's say we will call this the interval which ends the last as the first vertex to color, right? And then so next somewhere it ends like that. You just order these intervals in the order in which they end. Their starting point can be anywhere. For instance, this is the last one which ends, but it may be starting very far here, but many of these things may be ending earlier and all. The order of the big starting may not correspond to the order of the ending, right? Ending point. But we will order them in the way it ends, right? The where it ends, depending on where it ends. And decide to color this interval first. Decide to color this interval first. Okay. And then after that, we go to this interval and we want to color that. So, our plan is just to follow a greedy strategy. So, when you follow a greedy strategy, what should you worry about? That means whenever you are about to color the next vertex, you should see around. See around means its neighborhood you should see. You should not worry about what you have done for the entire graph and all. That's not even important in a greedy strategy. It's a local decision in the sense that you are just, for each vertex when you are about to color, you are only looking at its neighborhood. And in the neighborhood, you see which all colors are used, right? Suppose you see color number 1, 2, 3, then what should be the color you should be giving this thing? You should give the least available color, the fourth. Suppose you see 2, 3, 5, then you should give 1 because 1 is available, right? You just look for the color which is not used here, but least number. Suppose you have given numbers to the colors, right? So, this is the greedy strategy. Then if you keep doing this thing, you will get a coloring. Now, only thing is to prove here that the number of colors you use will be only omega here. By the way, yesterday I just asked this question. If you do this greedy coloring in a general graph, what can you tell about the number of colors you will use in the worst case? In a general case, in the general graph, number of colors which you can use in the.
It's less than equal to delta plus 1.
Yeah, it is less than equal to maximum degree plus 1 because in the neighborhood you are going to see a maximum delta number of neighbors, right? Wherever you are, because maximum degree is only delta being the maximum degree, and then you count. So, even if you are unlucky to see all different colors there, then also you are only using up delta colors. No, the next color will always be there. One color will be left if you have left delta plus 1 colors. If your palette has delta plus 1 colors, then one color will always be available. So, in a general case, this kind of a greedy strategy will give you delta plus 1. Now, our claim is that in this interval graph case, if I do this thing, this coloring in this particular way, I will be able to get omega colors. See, when I talked about delta coloring a general graph, one thing I did was to just take just another vertex which is not yet colored and color it now, right? But there one thing which is very loose in the sense that which I am not very careful about doing is that which I did not decide the next vertex to color with any particular rule, right? I just took another one, select another one, that is what I did, right? But the point is that if you, sometimes it is possible that if you are careful in selecting the next vertex, maybe you can make use of the structure like better. So, don't you feel like that? Because, so if you want to color using less than delta plus 1 colors, maybe if you are careful in choosing the next vertex, sometimes you can do better, right? Say for instance, I can ask you this simple question. Suppose your graph is not regular. That means there is at least one vertex which is less than maximum degree. That means its degree is strictly less than maximum degree. Not that all vertices are equal to maximum degree number of neighbors, right? In that case, can you tell me how to order? If you had selected the way to color in a more careful way, probably you can do little better than delta plus 1. You can do it with delta colors. Can anybody quickly see why that is like that? Because if you select the next vertex to color, because you somehow have to make sure that every time you select a vertex to color, you only see delta minus 1 neighbors in the already colored vertices. That means you have to order the vertices in such a way that you never come to the situation that you take a vertex, by that time all its neighbors are already colored, or but it should be like that, no, last vertex, right? When you come to the last vertex, all its neighbors are already colored, right? But then we have one condition, that all vertices are not delta degree, right? So what should you do? This last vertex, we should make sure that is that special vertex, or is that vertex which do not have delta neighbors, only delta minus 1 or less neighbors. That should be kept for the last position. Now you take the remaining graph, but the good thing is now the last vertex has gone, so that if you look at the induced subgraph of the remaining vertices, its degrees will now at least some vertices will reduce its degree, right? So there should be some vertices which has degree less than delta, right? So you can keep one of those things for the second last position, right? So this is it's a reverse thinking, right? And we will keep it for the second. We will color in the end only those vertices, but we will say I'll keep the less than degree delta degree vertex for the last coloring, and this one, next one I pick last but one position, like that, right? You can make this order from the back to like which should be colored last, and then which should be colored last but one, like that, right? So we can color. So there are some technical things, but you can do it for the maybe your tutorial session or something like that. But you should see whether will you get stuck, if at all, what is a possible reason if you are getting stuck, right? But it's true that you can actually color using delta colors. In fact, delta plus 1 colors are only required for very few graphs. Not on non-regular graphs, definitely you can do. Even for regular graphs, there are only complete graphs and odd cycles, which requires actually delta plus 1 colors, right? If it is a connected graph, if you're talking about connected graphs. But the moral of the story here is that what matters is that ordering of the vertices, right? The order in which you color matters. Which vertex is colored first, the second vertex which is colored, and so on. Here, this is one special situation like that. I have ordered the vertices according to a different rule, because there are intervals here. So I took the first vertex to be colored as the one which ends last, right? And the second vertex to be colored as the one which ends last but one, right? Like that. The order of the ending, the brackets, right? In the reverse order of the ending brackets. Now, my claim is that, so the same kind of greedy coloring is done now, but in this order, right? Now, my claim is that whenever I take a new vertex to color, maybe here, the neighbors I see, the neighbors of this vertex, which are already colored, the neighbors of this vertex which are already colored will indeed have this property that they form a clique, and along with this they form a a clique with one more vertex, right? So therefore, but I will be using only that, suppose if I had omega is my largest clique, and if I had used, suppose my palette has omega colors, right? Then because whenever I am about to color my new vertex, I look at the neighbors, I count my neighbors, right? And including me, the total number of vertices in the neighborhood is only at most omega. Then means I can always color using omega colors. So for that, I have to show that my neighborhood is always a clique. Not a neighborhood, the neighborhood which is already colored, right? The neighborhood which already got colors will be always a clique. How do you show this thing? So, because this is the new vertex I am going to color here, I can see the ending point somewhere here it will be starting, I do not care. But I know that all the vertices which got colored earlier are ending after this, maybe here, 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 something like that, right? Not before this, right? Because if it is ending here, you won't be taking it for even coloring, right? So, they are all ending this side, so they all got colors. But among them, which are the neighbors of this? Only those of them which started before this point only can be neighbor of this interval, right? Because if this vertex, this thing started here, if this was the interval, this will not even intersect with this, right? Then therefore, I do not have to worry about it because that is not my neighbor, right. So, among these things which are ending after this thing, only those which start before this thing can be neighbor of this, because then only it can cut with this, right, is not it? Then only it can intersect with it. So, that means all my neighbors will be starting somewhere beyond to the left of this and will all be ending after this thing. That means they all cross here at this point. They all pass through that point. If all those intervals which are in the neighborhood of this vertex which I am going to color and already colored are such that the intervals will have to pass through this particular point. That means they form a clique because they all share that common point, no? Because they all intersect with each other pairwise, right. So, because they have everything have that particular point in them. So, therefore, that will be forming a clique, and including this vertex which I am going to color will be forming a clique, and therefore, the number of vertices in the neighborhood of this new vertex union this vertex, right, will be less than equal to omega, because omega is the cardinality of the biggest clique, because the biggest clique itself can have only omega number of vertices, and how is it possible that? So, we will never need more than omega colors, right. So, we managed to color with at most omega colors. You know that you cannot color with less than omega colors, because at some point of time that omega clique itself will be coming and it will be requiring that omega number of colors. So, we have done with the optimum number of colors, that means the best possible coloring we have got it, right. So, this is also one example where the greedy algorithm works so perfect, right. So, usually we tend to think that greedy algorithms are bad, maybe bad, right, but there are situations where greedy algorithms work perfect, right. So, this is one such situation, the greedy coloring is working. The coloring otherwise is a very algorithmically very tough problem, in the sense that it is all this NP hardness and approximation hardness, everything is like coloring is one example where it is, you might have learned about approximation hardness and all, right. It is difficult to approximate within n to the power 1 minus epsilon or half minus epsilon, I forgot. It is very one of those the toughest layer, right, too hard to approximate even, right. So, won't even get any reasonable approximation factor for coloring. But then you see there are these special classes of graphs, the coloring becomes so easy because of certain structural features, and even simple greedy algorithm is giving you the optimum coloring, right. So, interval graph coloring is polynomial time efficient, very efficiently can be. So, the questions like this classroom allocation we did yesterday, that is very easy to do, right. In fact, all these hardness issues does not even come there, right. If you really have a problem like that with time intervals and we want to schedule and minimize a resource, you can actually model it as a graph problem, and it will, if it happens to be, it will happen to be an interval graph, right, because each of these things, lectures or meetings or whatever, it's all time intervals. Maybe in a factory you are asking for a machine, right, and I want for this job I need this time. You may book a slot for you, right, for your work, but somebody else may book a slot, but both the job cannot be done at the same time, right. So, then it is conflicting, then you need another machine, right. So, you can draw the conflict graph, but that will be an interval graph, right. So, because it is about every work is a time interval, right. So, yeah, it can be time interval, it can be like the interval of a sequence of lines in a intermediate code generated by a compiler or anything which can be an interval, right. So, there are many situations where this interval system comes in. Then in that cases, the coloring problem is the minimization of the resource, right, which is that whatever resource you are trying to compete for, that is we want to get to minimum number, because usually the resource is costly. That's why everyone does not have a machine of, because you have to go somewhere for into a central facility and use it, right, or maybe you need to minimize the number of registers in a chip or CPU or whatever, right. So, therefore, but these questions turn out to be in fact easy to, like, algorithmically easy, though in spite of the fact that the general problem in of coloring in general graphs is quite a hard problem, NP hard, approximation hard, everything, right. So, we need not get discouraged all the time. Many times the setup in which we work for our problem may have its own structure. Many times with some adjustments it may work out to be quite doable, is what I am saying. Okay. So, this is about the interval graph coloring. Any other question on this thing? Anything, any confusion, any? So, now let me try what will be the alpha perfection of interval graphs, or the chi perfection of co-interval graphs, complements of interval graphs. So, can you tell me what is alpha of the, at least you can visualize the alpha of the interval graphs. How will it look like? An independent set in an interval graph? It will look like intervals which do not touch each other, right. So, it may look like intervals like this. So, this is one interval, another interval, and then another interval, and another interval, and so on. This kind of a set of intervals will form the independent set. So, you have to take the biggest such collection. So, that is the maximum independent set. So, if I claim that its clique cover will be equal to the same as, it is the same as the maximum independent set, can you convince yourself about that? How will you see that?
Because those which are independent over here will intersect in the complement.
Right. So, one thing you can do is the same kind of strategy. Maybe you go from, say, this time this end to this. What I will do is I will create one. So, the first interval which ends, right, this is the first ending point of any interval. So, now I will take this interval and put it, I will make a collection of things which are independent sets. So, I will add it to my independent set, this one. But if I am adding this, what should I remove then? All the things which are adjacent to it should be removed, because now those things cannot be added to that, no. So, but those things which are adjacent to it should be starting before this thing and ending after this, because we have taken the interval which ends first as this one, that is what is gone, because other intervals cannot end here, right. So, they should not all end here, and they all start before this thing, otherwise they will not be neighbor of that, right. So, now all these things are thrown away, but interesting thing is that what is thrown away is forming what? A clique, because they all should pass through this point, right, because they start before this thing, end before that, including this vertex which I added into this thing, they form one clique. So, actually when you add one to this independent set, you like roll up all these things like that vertex and its neighborhood, and say that, okay, I add, this is my collection of cliques, I will put my first clique. So, I will put x1 here, so I will put k1 here, all these things. I will just pick a ball and put it into that. right? Then what I do? So once these are all gone, I will see some other a smaller interval graph here. But again, you do the same thing. You will look for in the remaining thing. You look for the interval which ends first, right? With the first and ending point, right? And take that thing, call it x2, and put it in this thing, right? Add it to the interval independent sets, right? Now what you do, again look at this thing, which are the neighbors of it. The neighbors will be starting before this thing and ending after that ending point. Starting before the end point we considered, right? Just like this, starting before this thing and ending after that, right? And we cannot maximal independent set. If you do, by doing this thing, we will get one independent set, but we will cover all the vertices now by the cliques. So that's all you have to worry, because actually you get a clique cover. See, this is optimal in maximal or not, I don't know, but I know that this indeed covers, right? And the cardinality of this thing is equal to the cardinality of this thing. So that means I have created a clique cover, right, which is equal to the cardinality of the independent set, right? And now if my independent set I created was less than maximum, then it won't be true, right? Because then that means that there is another independent set which is even bigger than this, but I covered the all vertices with a clique cover which is having less number of cliques than that. But we know that all clique covers have to be bigger than or equal to any independent set in the graph, because if you have a maximum independent set, only one vertex from that should go to one clique, because if you are trying to cover an independent set with a clique cover, one clique can cover only one vertex from that, no? Because it's after all it's independent set. Now two can go to the same clique. So any clique cover should have at least the maximum independent set number of the vertices, number of vertices in the maximum independent set, number of cliques in it, right? So if it so happens that this clique cover has exactly equal to the number of vertices in this independent set, that also means that this was a maximum independent set. Though we did not really try to make it maximum, right, but it will have to be maximum, because the clique cover is actually covering all the vertices, right? That number cannot be actually smaller than the maximum independent set, and because this number is equal to the number here, so that should be maximum. That's the point. Is it clear to all of you? Repeat again means the why, what aspect do you want to repeat? The algorithm. So this is also some kind of a greedy algorithm to collect. Yeah, that's also a little surprising. What we have done is a particular kind of greedy algorithm is used to make a maximum independent set, right? It's very clear that you can make an independent set, but why a greedy algorithm should get you a maximum independent set is not clear, but it so happens that you will get it, right? So what we did is we just looked at the interval graph and looked at where each interval ends. Now once you draw this interval graph, you can see which interval has an ending point, the earliest ending point among all the ending points, which is the one which is ending first, and pick up that interval, right? See, note that when I picked up this interval as having the first ending point, it does not tell us anything about where it starts. Maybe it just starts here and ends. Many other things are starting before this thing, right? But that we don't care. We only worry about which interval ends first, right? And that interval is what I am picking up, right? And then I am putting it into my basket of independent set, because I am making an independent set, right? First I will add it to my independent set basket, right? But then the point is that as each time I add a vertex to my independent set basket, I should make a contribution to my clique basket also, right? One for one, right? So what I do, how do I get my clique? So I look at this point, right? I will see the vertices, the intervals which are passing through this point. All of them will be forming a clique, right? Because they all share that point, right? there should be clique, including this one, what I put there, right? And that they roll up together and make a clique, and that's a clique that I'll put as first clique. The point is that this way I have collected all the intervals. See, there won't be any interval which starts here and ends here, right? Because we took the first ending place. So therefore, anything which started before this thing is going beyond this thing. So all those neighborhood will be captured, and so therefore, if at all, so now once I remove this clique, all the things now what is remaining are ending beyond this. This point is over, right? Nothing will be there before this thing, right? So if at all any intervals are remaining, they are all ending before this thing. Now you look only at the remaining intervals, right? Now look at the one which ends the earliest, I mean the same kind of thing, but in the remaining intervals, right? There you can call it the second interval selected, right? X2, that will be added to my independent set basket, right? And the same thing, I have to find a clique now for that. The same idea. So I look at that ending point, and all the intervals which are passing through this point will be collected now, right? And I roll them into a clique, and then put it as the second clique here, K2, right? And then I'll keep on doing this thing. By the time I finish off my intervals, so at some point of time, all the intervals will disappear, right? So I say that this is my independent set I created, this is my clique. So the cardinality here is equal to cardinality here, right? The point is this is a clique cover, so and this is an independent set equal to the cardinality of the clique cover. So that should be a maximal independent set, because no clique cover can have the cardinality strictly less than any independent set. So it should be the maximum, you cannot go below the maximum anyway. So you have gone and touched some independent set, so that is it. So this is so one, I guess from all these things, what you should understand is these interval graphs are quite nice graphs from algorithmic point of view, from structural point of view. They allow you to design algorithms easily, right? So typically if you have a problem, algorithmic problem or structural problem or whatever, so and if you are unable to find a solution, typically it's a good idea to try on interval graphs to see whether you can get a solution for interval graphs itself, because they are reasonably good class, big enough, well popular enough, and also some structural sophistication is also there, but still they give you a lot of grip, right, to think about. So many times there is good structure that algorithms become polynomial time and all that. In general, usually many questions have only like you don't get a polynomial time algorithm, but here we do get. So it's very useful when you do research. It's very useful to try out something on interval graphs and see whether it works like that or not, right? Okay, now I guess I have introduced the interval graphs, and so I have shown that interval graphs are chi-perfect and alpha perfect. That means interval graphs and co-interval graphs both are perfect. Now what? Now I will take the next class, class of graphs, namely the chordal graphs, right? The chordal graphs is actually a special, a superclass means something which properly includes the interval graphs that we have already seen, because all interval graphs are chordal. But does it mean that all chordal graphs are interval? Definitely not. It's one way it's correct, the other way is not correct. So, but let's look at the chordal graphs. So it's very, very simply defined graph. It just says that all those graphs which do not have a chordless cycle of length 4 or more is chordal. That's all it says, right? That means if you take any cycle in the chordal, it may be some 5 cycle, then you should get a chord for that, right? If you find a 10 cycle, definitely there should be a chord. That's all it says, chordal graph means, right? So, what kind of cycles will not have a chord, may not have a chord? It is only the triangle, but the triangle do not even have a place to have a chord, right. So, therefore, chordal graphs are very specially defined class of graphs, namely chordless cycles are not there, right, with length 4 or more. You will connect this statement immediately to the strong perfect graph theorem, because that also based on induced cycles and holes and odd holes, no. But that's oddness is there here, but this is a much more lavish condition with respect to the strong perfect. There we have to avoid holes and anti-holes, but odd. But here anti-holes we don't care, right, but we have to avoid all holes, even and odd, right. Instead of anti-holes we have added even holes also here, avoiding, right. So, this becomes a special class of graphs, right, no holes, odd or even, right. Anti-holes I do not care. So, now my point is that chordal graphs are also perfect, right. So, this is see, for instance, if your strong perfect graph theorem is there, it's okay, because yeah, I do not know, you can try to see, suppose you know strong perfect graph theorem, can you show that chordal graphs are perfect or not, right. So, because you have to show that they do not have anti-holes, right. The holes anyway do not have by definition. So, odd holes do not have the odd anti-holes, but you can try it. But let's go by classical thing, because all this strong perfect graph theorem was proved much later and with big machinery. But actually, the chordal graph theory is much more simple and easy to understand, elegant, and it was there for quite some time, right. So, so yesterday I gave you one starting lemma for chordal graphs. So, they had written it on the, I do not know how many of you tried it out, right. It talked about a interesting property of chordal graphs, namely the minimal separators. The minimal separators of chordal graphs have to induce what? A clique, that is what it told. A minimal separator, any minimal separator has to induce a clique. But by the way, what is a minimal separator? What is a separator? Actually, a separator, vertex separator. A separator means it is a collection of vertices which you remove from the graph will separate the graph. There should be at least two pieces after the removal. I mean, you should not count the vertices which are removed, right. The removed vertices disappear, but now after removal of those vertices, you should look at the graph and it should get disconnected, right. So, this is a separator. Are there graphs which cannot be separated at all? Whatever you remove, cycle you can remove. You just remove two vertices, you will get somewhere in the middle. Complete graphs cannot be separated, because whatever you remove, the remaining things will remain connected, right. But other things can be separated. For instance, even if one edge is missing from the complete graph, you could have removed the remaining n minus 2 vertices, and one vertex will go to this side, the other vertex will go to this side, right. So, this is a notion of the separator. It is a very intuitive notion. What is a separator, right? That which can separate is a separator. Now, we can talk about minimum separator and minimal separator. There is a difference between minimal and minimum, right? Minimum separator means what? Absolute minimum. That means the number wise, the minimum number of vertices that you have to remove so that it gets separated. If it is non-complete graph, you can separate it. So, which is the minimum number of vertices you need to remove so that you can break it into at least two pieces. The remaining things can be into 2 or 3 pieces, 2 or more pieces. A minimal separator, on the other hand, does not talk about absolute minimum. That is minimal. Minimal with respect to subset wise minimal means what? Minimal separator means if you find a separator, it should so happen that nothing inside it should be able to separate. I mean, no subset of it, no proper subset of it should be able to separate it. That means, suppose this is a separator, and some pieces come if you separate. But then I try to remove only this much of it. It should not happen that now we have, so we separate this, there should be a connection through this thing. Understand, right? So if you want to really cut it, you should remove all of this thing. No proper subset of it should be able to separate it, right? In that sense, it's minimal. So even if one of the vertices from that you leave out, then the graph will still be connected. So always this minimal, minimum, maximal, maximum, there is a little difference between some meaning difference will be there in that when I use. Now, like one question we told, we gave you yesterday. So a minimal separator has the property that any vertex in the separator, for instance, if there is a vertex in the separator, it should be connected to here also, here also. Suppose it made more components, then to all the components it should be connected to every vertex. Why is it so? So our claim is that it's not possible that there is some vertex in this minimal separator that it is connected to a few of the components which results, but to some other component it is not connected. That is not an option. Why? Because I could have removed that vertex. Suppose this was not connected to this, then I could have removed this vertex, right? And sorry, not this vertex. Right, I would have put all these things. See, this will I'll keep here, right? Because this is connecting all these things. I'll keep this thing, but still this piece will run away, right? So this will fly away because there is nobody which is holding this, because this was connected only to these people, not to this, right? So when I remove all the vertices from the separator other than except this one, I'll keep it there. Then I still get a separation. Why? Because this piece nobody is holding now, right? Because this person is not able to hold that particular component. So therefore, the responsibility of holding the components is for everyone in this minimal separator. For every vertex should be holding every component, right? Otherwise, I can cheat by removing all other vertices from the so-called minimal separator, but keeping that particular vertex there. But still that particular component which this guy is not holding will fly away, right? So therefore, I will get a separation. So that's a very simple consequence of the minimality, right? Minimal separators. I hope it is fine, right? Why every vertex should be connected to all components that results. Now this will be used now to show that a minimal separator, any minimal separator of a chordal graph should induce a clique. Suppose this is a minimal separator. So I just draw two components. Now suppose this is not a clique. This S minimal separator is not a clique. That means there should be some two vertices here, right? So if there is only one vertex in the minimal separator, then it's by definition a clique, right? If there are two vertices, then that should be an edge. If there are more vertices, all pairs should be connected. Suppose there is a pair which is not connected, like this. Then what will I do? I will look at, this is X, this is Y. The X will have a few neighbors here, right? Definitely, that's what I told. Y will also have a few neighbors here. And X will have a few neighbors here. And Y will also have a few neighbors. That's what I told now. Not necessarily just one, it may have more neighbors, right? Now what I do is, I'll first try to see whether there is anything common here. Suppose there is a common neighbor for this and this, and there is a common neighbor for this and this. Then what does it happen? If there is a common neighbor I can see here and here, then what happens? Yeah, then we get a fourth cycle which is chordless. Why is it chordless? Because there is this chord is not there and this chord is not there. Why? Because they are on different components. If this edge was there between them. When I remove this thing, why is this component separated from that component, right? Because there is this green edge going from here to here, that will be holding them together, right? So therefore, the very fact that this is separator, there cannot be any edge going from this part to this part, right? So this 4 cycle would have come, but it may so happen that there is no common thing here. So it may be just that this, yeah, there is this portion and this portion is supported. But still I can see from this set to this set, there will be the shortest route, right? Shortest route, smallest route. And then definitely I can connect like this. Similarly here also. This is going to be a chordless cycle. Do you agree? Of length more than 4 now. Why is it so? See, this chord is not there anyway. There cannot be any chord from this side to this side. But can there be chords here? Why? What? It's a connected component. Then, but still I am claiming that there cannot be any chord because I took a shortest path. That's the main thing. When you want a chordless route, what the best thing is to take a shortest path, because on shortest path you cannot have a chord. Why? Because then I'll short circuit that, no? So I will just jump over that, no? For instance, if this is the shortest path and there is some chord like this, then why do I go like this? I can rather jump like this and go, right? Why is this the shortest path from X to Y, right? So shortest path is kind of induced paths. Shortest path is induced paths. That means there are no chords. Means if you take the induced subgraph on a shortest path, the vertices of the shortest path, you will simply get that shortest path. There won't be anything else. No other edge will be there on that. Because if there is any other edge, there is a shortcutting, right? Possible. So this from here to here, we have taken the shortest route. So from here to here, we have taken the route. Among all these vertices, 2 vertices, the shortest route is what I should take, right? So therefore, I can connect like this, and overall, there is no chord from here to here. There is no chord from here to here. There is no chord from like this also, because then I would have taken that, right? It's actually the shortest route from this, the entire thing from here to here through this part is what I mean, right? Similarly, the shortest route from here to here through this part, right? So therefore, that will be a chordless cycle. So, but we know that chordal graphs do not have induced cycles of length 4 or more. So therefore, this assumption that this edge was not there is wrong. So this edge should be there. So this should be a complete graph now. Okay, this should be a complete graph now. So this is a very interesting property of chordal graph, that all minimal separators should induce cliques. All minimal separators should induce cliques. Now, the good thing about this presence of a minimal separator like this, the good thing about having a minimal separator, or meaning all minimal separator being cliques, is that using this thing, we can get some very interesting thing in any chordal graph, namely the simplicial vertices. What is a simplicial vertex? When we call a vertex in a graph a simplicial vertex, if its neighborhood induces a clique, right? If you take that vertex and its neighbors, it should just give a clique, and then that is called a simplicial vertex. So for instance, in interval graph, there is always a simplicial vertex. Have you noticed that? I mean, a vertex whose all neighbors are forming clique. So which is that simplicial vertex? Tell me one simplicial vertex in an interval graph. You have seen it many. Highest degree, no.
Which ends the last.
See, ends the?
Which starts the first.
Yeah. For instance, this kind of a vertex is simplicial, because which is the interval which ends first, right? Because any other neighbor of it should be starting before that, but should it be ending before after that. So they are all crossing this vertex and it's a clique. See, if you had picked up some interval in the middle, that may not happen, because so many things may start here and go here, right? Many things may come from this side and end, right? This will form a clique, this will form a clique, but then they may not have any connection between this part and this part. They may form two different cliques, right? In fact, there can be some things in between hiding inside also, right? In an interval, you can always have many this kind of things, right? Short intervals which are inside and which are actually not touching each other at all. You can have very large number of independent set itself in the so if your maximum degree may be like that. For instance, I can show you an example like see, look, this is an interval graph. How does it look like? This will be the interval graph. This will be the graph of what? This is an interval graph. If you draw the graph, what will be like? So this long interval become this middle vertex, and look, star. So maximum degree vertex is nowhere near being a simplicial vertex, right? Because they are all are independent set in fact. But on the other hand, if like he told, if you go to this end and take the interval which starts the first with this first ending point, and then all the neighbors can only go to this side, and nobody can hide inside also. Why? Because if somebody is hiding inside, that interval is the one which is ending before it, no? So that is why a simplicial vertex is there. Now this presence of simplicial vertex for interval graphs is clear to you, but we are claiming a very stronger property, namely all chordal graphs have a simplicial vertex. Not just interval graphs. Interval graphs are chordal graphs, but all chordal graphs will have a simplicial vertex is what we are saying, and we prove it by induction using this minimal separator concept, right? Induction, we can do this thing. We can just assume that for small graphs it is true. For instance, one vertex chordal graphs it is true. Definitely one vertex chordal graph means just one vertex, right? And two vertex chordal graphs it is true, right? You don't yeah, definitely it is true, because it's an edge or even two different vertices. So there is a simplicial vertex there. So small numbers you can easily check it, verify it. So let's assume that for smaller chordal graphs it is true, right? Induction on the number of vertices. Now this thing is, you take one chordal graph and consider a separator of that. Maybe this is a separator and it separates at least two components, maybe more components. But you may say that some chordal graphs may not have separator. What kind of chordal graphs do not have separators? Complete graphs do not have separators, but complete graphs do have simplicial vertices, no? All of them are simplicial vertices. So then we don't have to worry about it, right? Now, this is a separator S, and this is say G1 and this G2. That's what the two components it gives when I separate it. Now you see, if I take this part, right, I can apply the induction hypothesis. And what does the induction hypothesis say? There exists a simplicial vertex in that. See, look, if that simplicial vertex which should exist, see what I did is I included this part and this part. Now you may think that why I am including this also into this thing. I could have taken this alone, right? But this may be just single vertex also, right? Just a single vertex, that's not enough. So because some of its neighbors may be here. So if it so happens that I take this thing, I get one simplicial vertex here, and if all its neighbors are here, then this is already a simplicial vertex, right? Isn't it? Okay. But what is wrong? All these things will not be enough, because typically this vertex may be here. That means some neighbors are in this part, but some neighbors may be here. Then what is the problem? Induction hypothesis only tells me that this portion I have a simplicial vertex. That means it has to worry about only the neighbors on this portion. If there are some neighbors here, there need not be any connection between this, and there are no connection between this and this, right? So therefore, they won't form a clique. Are you following what I'm trying to do? I'm trying to do the trivial induction. So I know that all smaller graphs it is true. I can assume that there is a separator in the graph. I took the separator, and then I saw one part and the other part. So if you want, you can try. Okay, you can take a big piece, big connected component, and try to find a simplicial vertex there, which is definitely there because smaller graph, right? But then unfortunately, if I take any simplicial vertex in this thing, which is promised, but it may have, but when I put it in the context of the bigger graph, it may have some neighbors to outside of it. And induction does not tell anything about that, right? Because those neighbors may not have edges to the inner neighbors, right? But I want full now, right? I want that neighborhood from this part also, the other part also. So even if I had taken these two pieces together, it will not work, because because if I got a simplicial vertex in this portion, and then I am okay because all its neighbors are inside. But then if I got the simplicial vertex inside this, some neighbors may be there, right, on the other side, and there is no connection, there is no edges between this and this. So now how am I going to make this induction work? Like I would try this thing. So I hope you understood what I am trying to do. An induction, you all know how to do induction, right? You have learned it well. Now I want you to try to make this work. For 5 minutes I will give you, because it's a good exercise. So at least I believe that this is a good exercise in doing an induction proof, and see to understand how some hurdles like this is overcome. So you need to prove that there exists a simplicial vertex in any chordal graph. And you know that for small values of n, the number of vertices, it is indeed true. For one vertex chordal graphs, two vertex chordal graphs, it is true, right? Now, I even gave you the separator idea. So I take a separator, because if the separator is not there, it's true anyway. Take a separator, and then I remove the if I remove the separator, I will get multiple maybe two components or maybe more. Then I know that any chordal graph which is smaller than the whole, you will get a simplicial vertex. But still, I am finding it a little difficult to make it work for the full graph, because I don't know where exactly that simplicial vertex will stay. Wherever I get that simplicial vertex, because I applied the induction on a smaller graph, so whatever vertices I left out, this particular simplicial vertex may have connection to that now. So may claim more neighbors from outside, and then these neighbors should collectively form a clique with the neighbors in the inside, right? So why it's not obvious how it works. So are you trying it, or so are you following it? Otherwise, it's a futile exercise if you are not if you're not even trying to understand the question. Anyone has to say something about it, how the induction may work? What induction on the G1S and G2 together. But together, how will you apply? To apply induction, you should at least reduce one vertex, because induction works like that on smaller number of vertices. Hypothesis only gives anything for smaller number of vertices. Now we had to extend to one more. So this is the full graph. So if you throw away even one vertex from here, fine. What? If you remove a vertex from a separator, it will still be a separator. So
This will be a clique and it will still be a separator, and this graph will stay a chordal graph.
this,
It will be a chordal graph.
yeah, still be a chordal.
Then we will use induction and then
Use induction and do what?
then there will exist a simplicial vertex in that graph, and it can't exist inside the separator, as we said.
Suppose it has a
It has a
clique, separator. So where will it be the? Suppose the simplicial vertex exists here, right? Yeah, in G. Suppose the neighborhood is like this, right? And but what if it had a neighbor here, which is you removed, right? This is the vertex you removed, right? Suppose it had a neighbor here, and this may not have any connection to these things, so it won't be a simplicial anymore, right? So I think you should try to make it work. It may, so you will see that it's a little tough, but you should try, right? Maybe, yeah, with some more ideas it may work, I don't know. But you see a very nice way to make it work, which is very illustrative, in the sense that sometimes this induction, the trick of the induction is that what is in induction, first you prove it for 1, 2, 3, n equal to 1, 2, 3, etc., and then you have an induction hypothesis, right? And then you extend from n to n plus 1 or n minus 1 to n, right? That's what you do. So suppose you want to prove something. Suppose here you want to prove that there exists a simplicial vertex. The suggestion is that instead of trying to prove there exists a simplicial vertex, try to prove there exist two simplicial vertices. I mean, that looks counterintuitive, right? Means if you cannot prove that there is one simplicial vertex, how can you prove that there are two simplicial vertices, right? Because one itself you are finding difficult. And not only that, prove that if it is a chordal graph, which is not a complete graph, non-complete chordal graph, then there exist two simplicial vertices which are actually non-adjacent, not adjacent to each other, not an edge, no edge between them. Two simplicial vertices such that they are not connected to each other, right? A pair of simplicial vertices which are non-adjacent. I mean, this is asking for too much. While one simplicial vertex was itself difficult, but still somehow it works easily, right? When I try to ask for more, why is it? Tell me why is it so? The philosophically, at least by the philosophy of induction, why it can happen sometimes. Though we are asking for more, we are able to prove the bigger thing, I mean stronger statement, while we are struggling to prove the weaker statement, right? But when the statement is made stronger, we are able to prove it. What is the reason for that? What is in induction that makes such a thing happen? I mean, you all know induction, how the induction works. You should be able to answer this question. That means if you have thought about induction, so you should at least might have noticed the feature of the induction which makes this possible. Sometimes when the statement is strengthened, you can prove it. Why? Philosophically, let's say, means why? Because induction try to make use of the induction hypothesis, right? For up to n minus 1, this is true. When I strengthen the statement, that strengthened statement is available as a hypothesis on n minus 1, right, for me to use. Earlier, when I had only a weak statement, only that weak statement was available to use up to n minus 1 also, right. So, now I strengthen the thing, then I know that in the smaller graph there exists, I can assume that there exists two simplicial vertices which is non-adjacent. Earlier I could not assume that. Now, when I ask for more, I also got more to work on, right. So, this is, for instance, now look at this picture again. So, now I am saying that in the smaller graph there exists two simplicial vertices. Say the picture is this thing. The smaller graph, this is G1, S, G2. So, take this portion. In this portion, there are two simplicial vertices, not one, and which are non-adjacent. So, my problem, if one of the simplicial vertices was here, I am done, isn't it? Because all this neighborhood will be here only, right? Because it is okay, because there is no neighbor coming from there. The problem was if the simplicial vertex was here, that means some neighbors can be here and some other neighbors can be here, but there won't be any edge from here to here. So, it won't be simplicial when in the context of the bigger graph. Now, I know that, but it cannot be just this, there should be one more, because I am assuming that two simplicial vertices are there. Where can the other be? Can that other also be here? No, why?
Because we have assumed that they are not.
Right, because this was, see, it's a non-adjacent pair of simplicial vertices, but this is a minimal separator and it's a clique. There should be an edge there, isn't it? There should be an edge there. So, this should be here, somewhere here. And that's enough. We got it, right? So, it's a very, very good trick that we have done. What we have, many times you don't notice that induction has such a power that when you fail to prove a certain thing using an induction, you can ask for a little more, and if you are lucky, you may be able to prove that. Counterintuitive, but that's because the induction assumption, what you can assume also become stronger then. As a hypothesis, what you are relying on, the hypothesis for n minus 1 up to n minus 1 is also stronger now, because you can assume 2 here. Earlier you can only assume that there exists one and that can be in the wrong place. Right now I can assume that there are 2, both cannot be in the wrong place. That's what. I hope you appreciated this, right? This is a good thing to keep in mind for those people who later want to use an induction proof. So, you should realize that sometimes strengthening the hypothesis will, strengthening the statement itself, trying to prove a stronger statement may help you. But you have to know how to strengthen, because see, just strengthening in arbitrary ways may not work, because that may not be true even, right? You may be trying to prove things which are not even true. You should go through the first stage and realize that, okay, this is my the hurdles, right, the roadblocks, and then to overcome that, if I add this extra, it may work, kind of. That will only come by going back and forth, but sometimes such things works, but awareness that such things may work sometimes may help you, right? For those people who really try to prove a thing, otherwise. So, if you never try to prove a thing, it does not make any sense. But as a good technique, as a those people who see as a induction as a good technique to solve things, it's a good thing to observe, right? So, what we have proved now is that in a chordal graph there is always a simplicial vertex. In fact, there are 2 simplicial vertices, and these 2 simplicial vertices can be there should be 2 vertices at least, right? So, the connected chordal graphs, and what we are telling is If it is non-complete, these two simplicial vertices can even be non-adjacent. Now, okay, anyway, come back to the simplicial vertices. Forget about 2, that was only a technical thing, right. So, we have a simplicial vertex now in the chordal graph. So, then if we have a simplicial vertex, we can do a very interesting thing looking at what we did in the interval graph, right. So, interval graphs, when we colored the vertices, I wanted to get a coloring of the vertices of the interval graph in such a way that the number of colors used is equal to omega, the clique number, right. That is what we did. That is what we want to do it in the chordal graph also. We want to generalize that proof to this thing. But this is chordal graph, there is no intervals to rely on, right. Actually, it is more abstract because we do not have any pictures to rely on, right. But we want the concept to be generalized now. But what was it working there? It was an ordering. I could pick up an ordering of the vertices there, actually based on the ending points of the intervals, right? In such a way that every time I was about to color, when I looked at the neighbors which are already colored, they were forming a clique. That was the idea, right? Because then therefore, I know that I will have to use only that number of neighbors plus this new vertex, number of colors, but that is already forming a clique. So, it is always less than equal to omega is what I told, right, because the biggest clique is only omega. Now, if that is the situation, then same thing I want in chordal graphs. Not the pictures, intervals and those things are not there in chordal graphs, but drop the pictures, abstract out that only. Just abstractly, that only take that idea only. I want an ordering in chordal graphs such that whenever I take a new vertex to color, the already colored vertices which are neighbors of this vertex, that means already colored neighbors of these vertices, should form a clique along with this thing, right, should form a clique, should induce a clique. This is the property. If I get that property, the same argument works, right, because then keep on coloring, then I am just taking the greedy color, next color. So, therefore, I will never use more than omega plus 1 colors, because see myself and my neighborhood is forming a clique, at least already colored neighborhood is forming a clique, right, it is at most omega. So, but do we have such a ordering available in chordal graphs? So, what helps us to create such an ordering? Simplicial vertices. How should you create that ordering now? The simplicial vertex should come where? In last. Now, remove that simplicial vertex. Now, look at the remaining graph, which is again a chordal graph, because it is all induced subgraphs of chordal graphs of chordal, right. Now, there again there is a simplicial vertex. I mean, minusing this removed vertex, because if you do not really worry about what vertex you remove, in the remaining graph there should be another simplicial vertex, no? Because every chordal graph should have a simplicial vertex, and put it in the second largest place. Not that that may not be a simplicial vertex with respect to the original chordal graph, because this last simplicial vertex may not form the clique, right, because it may be connected to this thing and along together it may not form. But then if you discard that, the remaining is again in the remaining graph it is a simplicial vertex, put it in the second place, second last place, and now remove that also. Look at the remaining n minus 2 vertices, and it is again a chordal graph, there should be a simplicial vertex there, pick up that and put it in the third place, and so on. You create the order in the reverse way. Now, this is like that, right. Now, coloring will happen from the other end, right, the last the last one to be put in the sequence will be colored first and backward. So, then you know that every time I am about to color a vertex, I will be looking at the already, because that is a simplicial vertex with respect to the already colored neighbors, already colored vertices of the graph. So, that means this position I will get the simplicial vertex of G, and in this position I will put the simplicial vertex of G minus, say suppose this is x1, So G minus x1, and this will be simplicial vertex of G minus x1 comma x2, and so on I will put. And the coloring will happen from this onwards. This will be colored, this will be colored. So for instance, because when I am taking this vertex to be colored, so this particular graph, this is a simplicial vertex, right? So all the neighbors which are colored are only here because these are not yet colored, right? So they are forming a clique. So I can use this is a full, including this itself, it's a clique, right? Because it's a neighborhood only. So therefore, we know that we are now never going to use more than omega number of colors, right? The simplicial vertex is actually helping us, right? We can get this sequence such that in the induced graph of this particular vertex and the vertices to come later, I mean, which will be colored earlier than this, right? They will form a chordal graph such that this is the simplicial vertex in that. That's the trick. Anybody here who hasn't understood it? Any questions? Any questions on this? You can ask. By the way, this idea, this last thing we told, this ordering we created, the ordering of this sequence of simplicial vertices in the induced, not simplicial. So in between, if I take a vertex and ask, is this a simplicial vertex in the original graph? No, it's only a simplicial vertex in that graph, starting from that vertex and forward, right? So this is called a perfect elimination ordering. This is called a PEO, perfect elimination ordering. Perfect elimination ordering. And you will wonder, what is this perfect elimination? Perfect makes sense. Elimination ordering is what? Maybe you can say that it's eliminating the vertices. Eh? We are adding the vertices. We are eliminating the vertices, but it has to do something with the Gaussian elimination in matrices. You might have studied how we do the matrix in matrices when we try to find a solve the equations or maybe determinant or whatever. So we do that, make it upper triangular, right? Do the Gaussian elimination, right? So you can, because in a graph can be put as an adjacency matrix, and you can see if you don't want to create too many new entries when you do the Gaussian elimination, what should be the corresponding structure in the graph if you look? You can see that if this kind of an ordering is there, you won't introduce any new entries. Then zero entries will not become non-zero. I think you have to think about the matrix elimination and see, for instance, if I do it in the order of the perfect elimination ordering, why it does not make any zero to a non-zero. But I'll skip that, but you can, those people who are familiar with matrices and Gaussian elimination and all can think about it, right? Why this kind of a elimination ordering. So that is sometimes when very large scale like computations are done, like linear equations, solving system of linear equations when we want to solve. So this kind of things will come useful, right? Because there the challenge is to keep the memory requirement. If you have a large matrix, right, n by n matrix, so there are n square entries to be kept. But then suppose it's a sparse matrix, that means there are not many non-zero entries in the matrix. Then why do we keep all this zero unnecessary, right? It's a waste of memory. So we can keep only the locations wherever this is the place. But the nuisance is that when you do this elimination, you may make some zero to non-zero, right? When as you keep on doing the Gaussian elimination, then we need to give memory space for. Though we started with a sparse matrix, as we go on eliminating, it may so happen that we may introduce more and more non-zero entries, and that observation may not be useful at all. The sparse, maybe using full n square places. So we want to make sure that we don't introduce too many non-zero entries like that. But again, you can think about it. Anyway, it does not matter. It's a name, perfect elimination ordering. Now, this perfect elimination ordering is a very, very good tool for chordal graph, which kind of generalizes this thing which we saw in the interval graph, right. And now we know that there is that notion, and now let us use this perfect elimination ordering to show that these chordal graphs are alpha perfect. Means the same thing which we did for the interval graph. So, we want to repeat for the chordal graph, but now we have the tool, namely the perfect elimination ordering. What should we do? I mean, it's obvious. We just have to generalize what we did for the interval graphs. So, I think I am giving you some time to do that. Don't wait for me, because it's exactly replicating the thing, but with the more general tool, namely the perfect elimination ordering for chordal graphs. By the way, when did we start the session? 9:50? Okay, it's kind of time, I guess, right? Isn't it? Okay, with this exercise, we will wind it up for the D. But it would be nice if you can work this out yourself. There is no challenge, actually. It's actually repeating what we did for the interval graph, but now there is no interval structure, but we have to use this ordering, that's all. This is a concept which captured the essential details we use for the interval, that's it. So, therefore, generally, I hope those people who can quickly see might have already finished doing that. Very easy, right? So, you have to put one to the independent set. So, put the first simplicial vertex to the independent set and collect the neighborhood, which is a simplicial vertex. No, its neighborhood will be collected as a clique and put it in the clique cover. And then now in the remaining graph, take the next simplicial vertex, the earliest in the ordering, and put it in the independent set, right? And collect its neighborhood, and which is forming a clique, and put it in the clique cover. Like that, you can keep doing this thing. So, we will collect an independent set and a clique cover, which is having the equal cardinality, and we know that because they are equal, that's optimal, right? Because one has to be above the other, but when they touch, it has to be optimal.